Hi, good evening, everybody. So, my name is Ashaq Ilahi, and let me introduce a bit about myself. I did my master's from IIT Delhi in mechanical engineering. Thereafter, I had a brief stint with Tata Motors, and I was working in Daimler after that in automobile sector, where I was doing crash simulation. And after that, I was working in Whirlpool Corporation as a structural analyst. And currently, I'm working as a senior project scientist in IIT Delhi for DRDO project. Basically, I work in blast simulation using FEA simulations. So just I will stop the video and I will share my screen. So I guess my screen is visible. So going to presentation mode. So we will discuss today about strength of materials actually. So what is the reason for studying strength of materials? Basically, strength of materials refers to the behavior of a material when external forces are applied. So why we should study the behavior of materials when external forces are applied is we have to predict how is the material going to fail when forces are applied, and what are the parameters through which we can infer whether the material is going to fail or not. So these parameters are stress and strain. So we have to determine stress and strains of a material which is subjected to external loads, and then we can infer whether the material is failing or not. So for engineering point of view, it allows the ability of a component of a structure to withstand the forces. And from science point of view, it tells us what makes a material strong, and it helps us to design a better material. So in strength of materials currently for the BTech syllabus, we'll be learning mostly metals. Because like we can also study composite materials, polymers, plastic materials, etc. But metals is one of the most simplest kind of materials because the constitutive equation like stress strain relations for metals is much easier compared to other materials. So we're going to start first with metals, and then we will see later for other cases like plastics and polymers. So I will go to the next slide. So what are the properties of materials that we are most interested in strength of materials? These are elasticity, plasticity, ductility, hardness, toughness, creep, fatigue, and fracture. So we have to know all the definitions for these material properties from exam point of view because they asked these questions. So we have to know one-line definitions for all these material properties. So going to the next slide. So when a material is subjected, for example, we have a material here, and when it is subjected to external forces F, we have atoms in between the material. So whenever it is subject to a force, these atoms will try to pull this material inside. So these are kind of restoring force for this material. So when we remove the forces, the material will come back to its original position from the deflected position. So this is called elastic deformation. And after we remove the forces, if the material doesn't come back to its original position, then we call it's a plastic deformation because the atoms are permanently displaced in case of plastic deformation. So from design point of view, we don't want plastic deformation actually. We want elastic deformation because if plastic deformation is happening in a material, then we can say the material is yielding and it is not meeting our design requirements. So we can apply various type of loads in a structural component, like we can apply tension, we can apply compression. So tension will be the outward force, and we can apply inside compression as well. So other kind of loads such as shear force, torsion, bending, those kind of loads can also be applied actually. So these loads we will see as we discuss in the subsequent slides one by one. So going to the next slide. So now we will discuss two very important parameters, stresses and strain. So what is stress? So we have a component here and we are applying a force here, tensile force, and because of that the material will be deformed. So we can define stress as the restoring force exerted per unit area. So what is restoring force is that the interatomic forces here, they will try to pull the material inward. So this is the kind of restoring force. This is the external force F, and this is the restoring force, which is pulling the material inward due to the interatomic forces within the material. So this is the restoring force here, and divided by the area where the force is applied. So this will be the cross-sectional area here in this case, through which the external force is applied. So this is the cross-sectional area that we are talking about. So stress is the restoring force divided by the cross-sectional area. And what is strain? Strain is the change in length to the original length. Whenever we are pulling the material, we will get a change in length. And this is the original length L. So the ratio of the change in length to the original length is strain. So the unit of stress is Newton per meter square, Pascal or megapascal. And the unit of strain, it is dimensionless because we are dividing one length value with the other value. So we don't have any units for strain. Let's go to the next slide. So normally we get stress strain curves through a universal testing machine, UTS. So how does a UTS work actually? So for example, we have a specimen here, like a tensile testing specimen for mild steel. We will load this specimen in the tensile testing machine, and we will have some grippers here. These grippers will try to pull this material outward, and we will have some sensors here, like extensometer sensors and some load cells. Using that, we can plot a force reflection curve actually here. So we have force and we have the deflection here for this material. So it will be something like this, and then we can convert it to a stress strain curve. So strain, strain, and stress. And from this curve, which is generated from the UTS machine, we are able to know many properties like the yield strength, plastic strain, necking, fracture, Young's modulus. So all these properties we are able to know from the universal testing machine. So one more thing of the universal testing machine is that once we do the experiment, we have a computer attached to this UTS machine, and during the runtime we will get the plot for the stress and strain. As we do the experiment, we'll be getting this type of curves from this UTS. These are basically servo hydrocontrolic UTS machines, and now they're featured with computers from where you can get the stress strain curves. So let's go to the next slide. So before going to the next slide, a few more things I want to discuss here. So this curve actually is the curve for mild steel, and we can see some important points here, like up to this point, this is linear, the stress strain curve, and this point is called a proportional limit, where stress is directly proportional to strain. After this point, we will have a point called the yield strength, and beyond the yield strength, plastic deformation will occur. So beyond this yield strength point, whenever we're trying to pull the material will not come to its original state. So we can say that there is plastic deformation or permanent set in the material. And after that, we will get the ultimate tensile strength, which is the point where we get the maximum stress in the material. And after that, the necking part, we get fracture. That is when the material completely breaks down. And from necking to fracture, we have a decrease in the stress because the interatomic bonds are completely fractured during this part of the material. As a result, it dissipates the energy, and that's why we see a decrease in stress in the fracture. So in this part, from the origin up to this proportional limit, we have a linear part, and this part, as I mentioned, stress is proportional to strain. So if we take the slope of this part, stress by strain, we will get a value called the Young's modulus, that is E. And E is very important when we derive the constitutive relation between strain and strain. So if we don't have the value of E, then from this curve, we can get the value of E by finding the slope of this curve with respect to the x-axis. So just do a tensile testing specimen, get the curve and get the slope, and we get the Young's modulus. So these are the important points that I wanted to discuss regarding the stress strain curve from David's machine. So let's move to the next slide. So we have seen that we have a force versus deflection curve from our tensile testing machine. So this stress versus strain curve, it can be linear, where force is directly proportional to the deflection, or it can be non-linear of this form. So rubber and all, they exhibit non-linear properties, like where force will not be directly proportional to strain. So for metals and all, we have a linear property actually, up to the elastic limit. Let's move on to the next slide. So here we're going to discuss two important concepts: true stress and strain, and engineering stress and strain. So what are the basic differences between true stress strain and engineering stress strain? So whenever we are pulling a material with a force F, first we will get some necking in the material like this. Then after some time we will have a failure. If the material is ductile, we have a cup and cone failure like this, complete collapse in the necking region. So we can see at different instance, we have a reduction area. Here we have area A, here we have a less area in the necking portion, and here we have even a lesser area. So stress is equal to force exerted per area. This is our normal definition. So from here we can see what is the difference between true stress strain and engineering stress strain. So in true stress strain, we are getting the instantaneous area. This area is instantaneous. What do you mean by instantaneous? That is at any instant of time. For this scenario, we will take the area in this instant. For this scenario, we'll take the area here. And for this, we'll take the area here. So for all the three cases, our area is changing in this part. So we can say that the area is decreasing. So when the area is decreasing, our stress is increasing. That's why after this necking part, our true stress strain curve shoots up. This is the necking part and this is the necking part. These are the necking part. So since our area is decreasing, our true stress strain value shoots up. But in engineering stress strain curve, what is happening? We don't take the instantaneous area. We take the original area for all the cases. Even if the material is decreasing its cross section, we take the original area. That's why our area remains constant. So that's why what happens after necking, this stress value shoots down in engineering stress strain curve, because our area is same. That means it is with reference to the original cross section area. That's why our strain is decreasing here. So that's the basic difference between true stress strain and engineering stress strain. And these are basically empirical relations that we have to remember in order to convert engineering stress strain curve to true stress strain. Normally, when you do design problems, we get engineering stress strain from the supplier, and we have to use these empirical relations to convert it to true stress strain curve. If we do CA simulations, for example, in product design, we have to convert it to true stress strain because the solver supports true stress strain. And true stress strain will give you the accurate results because it is using the instantaneous area of cross section. So basically, this is what I wanted to discuss here. So let's go to the next slide. So here we'll discuss a property called ductility. So what is ductility? So ductility is a property of material with which we can draw it into thin wires. So we desire ductility actually, because ductility, if we have ductility, then the material will not fail easily, and we will have a kind of warning that the material is failing. So ductility is good. And basically, when you have a ductile material, our area under the stress strain curve is more. That's why a ductile material will have more strength compared to a material which is having a less ductility. Let's move on to the next slide. So another important property of a material is toughness. So toughness is the energy required to break a unit volume of material. Or we can say that toughness is the area on the stress strain curve up to fracture. So if we find the area under the stress strain curve up to the fracture point, then we will find toughness. So more the area under the stress strain curve, more is the toughness. Lesser the area under stress strain curve, lesser the toughness. So metals and all, they are ductile and they will have more toughness. Ceramics and brittle materials, they will have less toughness. They will break very early, and that's why the area under the stress strain curve is less. That is why they are less tough. So this is another important property. So one more property that we can discuss is the hardness. So hardness is the resistance to penetration or indentation. So if we try to resist something onto material, then we will get some penetration or indentation. So if we don't get any indentation or penetration, then we can say the material is hard. And if we get more indentation in the material, then we can say the material is not hard. So hardness means resistance to plastic deformation or cracking in compression. And if you have more hardness, we can say better wear properties. So that was actually all from my side actually. I hope you have understood the concepts today, and you can ping me or write to me if you have any doubts regarding today's session actually. So, okay, I would like to close the session for today. Yeah, bye.